For this module, we're going to have the continuous random variable. This lesson addresses the course outcome, compute the probability distribution of a random variable for both discrete and continuous data. The intended learning outcomes for these lessons are: 1. Determine the probability from the probability density functions. Determine the probabilities from cumulative distribution functions and cumulative distribution functions from probability density functions. Calculate the mean and variances for continuous random variables. Calculate the probabilities. Determine the mean and variances for some common continuous probability distributions. Understand the assumptions for continuous probability distributions. Select an appropriate continuous probability distribution to calculate probabilities for specific applications. Calculate probabilities, mean, and variances for some common continuous probability distribution functions. Approximate probabilities for binomial and Poisson distribution. For continuous random variable, instead of the probability mass function, we will be having the probability density function. We're going to take note of that as PMF. For PMF, this is for discrete random variable. So we're now going to have PDF. So this is for the continuous random variable. For continuous random variable, the probability density function is a function such that f of x is greater than or equal to 0. This is the same for probability mass function. The integral of f of x dx for all values where the function exists is equal to 1. And the probability that the random variable x takes values in between a and b inclusive is the integral of f of x dx from a to b. If x is a continuous random variable for any x1 and x2, the probability that the random variable x takes values in between x1 and x2 is just the same whether they are equal or not equal at the given boundaries, because the integral from a lower limit to upper limit of the same value is equal to 0. A histogram is an approximation to a probability density function. So this is the graph of a probability density function, while the cumulative distribution function is a function of a continuous random variable f of x such that the probability that the random variable x takes values less than or equal to x is the integral of f of u du from negative infinity to that limit x. Therefore, to solve the probability density function given f of x or given cumulative distribution of x is the derivative of the cumulative distribution function as long as the derivative exists. For the expected value of the continuous random variable, the mathematical expectation or the expected value of the random variable is the integral of the function h of x times f of x dx for all values where the function exists. Suppose that x is a continuous random variable with a probability density function f of x. The mean or the expected value of x denoted as or e of x is given by mu equal to the expected value of x, which is the integral of x f of x dx for all values of x, while the variance denoted by v of x or sigma squared is given by sigma squared equal to v of x, where it is equal to the integral of x minus mu squared f of x dx from negative infinity to positive infinity, which is also equal to um, the integral of x squared f of x dx from negative infinity to positive infinity minus mu squared. And the standard deviation of x is given by sigma equal to the square root of the variance. Take note that the law of expectation also applies such that the expected value of x is the mean. The expected value of a constant is that same constant. If a constant is multiplied to x, it would just be a expected value of x, or simply a mu. While if we have expected value of f plus or minus g, it is equal to the expected value of f plus or minus expected value of g. So therefore, the expected value of ax plus b is a expected value of x plus expected value of b, or a mu plus b. For law of variances, the variance of x is sigma squared. So if we will be multiplying everything by a constant, the variance of ax is a squared times sigma squared. If we are going to add a constant, if constant is added, it would not change the variance. Adding a constant or subtracting a constant does not change the variance. So the variance of ax plus b is equal to the variance of ax, because it would not change the variance adding a constant. So this is a squared variance of x, or a squared sigma squared. Sorry, it should be a squared. These are some of the references used for this video.